Hey class, Mr. Mohidian here. You're about to watch a much longer video going into this process into some more depth, but I wanted to give you a bit of a summary of an important part of this process that video doesn't go over, and that is the reverse power rule. So in a problem like this, which is new to us, we're seeing this big S shape, which is just mathematical instructions for you to take the antiderivative of the part that follows with respect to this variable right here. So that S is just mathematical instructions to say, if this thing is the derivative, what was the original function? Well, we know the original function was raised to the fourth power, and we know that because the derivative of this thing that I've written would be 4x to the third. In fact, that's a good way to start. I know this is not the answer because this is not 4x to the third, it's 2x to the third. So what number should have been in front here in order for that 4 that would come down by differentiation to become a 2? Well, naturally, that would become a 1/2. So if I take the derivative of 1/2 x to the fourth, I would get, by the power rule, 2x cubed. But that's true for any constant being added to this as well. If there was a +3 or a +7 or a +12 or a +5,000 here, all of those guys would vanish because the derivative of any constant goes back to 0. So the final answer we would say is 1/2 x to the fourth plus c, where c is any constant. We can generalize this process with an important formula form, which is called the reverse power rule, which I have written over here. If a is some constant coefficient and n is some power over here, then we can say that the antiderivative of this is going to be adding 1 to the exponent, as opposed to subtracting 1, and then dividing by that new exponent. And if there was a coefficient, of course, then that coefficient would stay along, some constant multiple, and then I'm going to add c to that, because any constant would have a derivative of 0. So this is called the reverse power rule. Important formula, more of a process to know. Now there is one caveat here. As you can see, n can be any power as long as it's not -1. If the power is -1, then as you can see, that creates a major issue down there. So this is the caveat for using this process. Let's look at a slightly harder example, then we'll get to the main video, which I will link to in the assignment description. So this problem, you'll notice right away, has two terms, and they're being added. So we can really treat this like two separate problems. One part is easy, one part is not as much. 4x to the first power is pretty easy. That's hopefully you can see that that would become 2x squared because of just the power rule. But if you want to go about this the long way, you have your old coefficient, you add 1 to your old power to get your new power, and you divide by that new power. And then, of course, that simplifies to give us 2x squared as promised, plus c, because, again, that constant being added could have been there, and any constant would not appear in the derivative form. The other part of the problem here, 4 cube root of x squared, is not quite ready in calculus, for calculus yet, so let's give it a slight makeover here and express that as 4x to the 2/3 power. And now when we apply the power rule, it'll be, the reverse power rule, we would keep that old coefficient, we would add 1 to the exponent, so 2/3 becomes 5/3, and then we would divide by that new the new exponent. So this would be, again, sort of a more complicated version of the term next to it, but what we can also do is simplify this a little bit, because what we have here is equivalent to 4 times the reciprocal, 3/5, because we're dividing by that 5/3, which would, of course, give us then 12/5 as our coefficient, x to the 5/3 power. So there's that term, there's the 2x squared, and that would be our answer to the original problem right there. So reverse power rule, going back to the main formula here, make sure you know it, and hope this helps.